Hi, today we will talk about STAR. STAR stands for Splited Transcript Alignment to a Reference. It's an alignment tool for RNA-seq. It can identify alternative splicing junction in RNA-seq. It's a free open software developed by Alexander Dobin and al. So the workflow of STAR is the following. Step 1, the user first supply reference genome and annotation file. STAR then will be its own index. By analyzing the standard genome, STAR can produce a surface array index for accelerating the alignment step. The indexing step only should be built once. The index file can be saved and reused. Step 2, user can supply RNA-seq read files. STAR will then map the reads to the genome and write output file, including alignment files and summary statistic. Since it's an open source software, everyone can download from the official site. For Linux and Mac user, there are two different methods to download it. For Windows user, it's slightly more tricky. I recommend to first install Sequin to have a Linux-like environment. And please remember to download the developer package as highlighted in the slide. Then after that, when you run Sequin, you can just type the command as the method 1 in previous slide, and you will start downloading STAR. Also, if you're using an Odyssey, you can just simply load the module as below. And please be sure to check to use the latest version. If you have any more questions regarding downloading, installing, or usage of STAR, you can go to the menu, or you can use the STAR help page. So I will now talk about the command. First, we need to generate index. The input, we will need a genome FASTR file and optional annotation file. So it can be from any source. The below example is downloading the genome FASTR file from Ensemble. It also downloads annotation file from Ensemble in the second part. Downloading an annotation file can help to enhance the accuracy of your library, so I recommend you do so. After you have those files, you can first create a directory for your index. Then you can run the following STAR command to create a genome index. Or you can simply skip it and use existing index, perhaps viewed by your coworker, or you can download it from the STAR website. Next, we'll talk about the mapping command. The input parameter will be really important are the read files. It could be single N or pair N FASTQ file, and the genome directory, the path to the genome index. It could be this from the step we do in previous slide, or it could be just downloaded. So the first example is using a single N FASTQ file, while the second example use pair N FASTQ file. So there are two file name in the read files in output, in the read files in parameter. For the output files, there are three types. First is the alignment file. It can be in SAM or BAM format depending on the user choice. And the other file is sj.ao.tab, which contains high confidence collapsed splice junctions in unit mapping. It's in tab delimited format. And there are three kinds of log file. We will then talk about the most important one, which is log.final.out. It's a summary of the mapping statistic. The first 4 lines will just give you describing the drop just ran. And what is important is the unique read section. Uniquely mapped read number refer to the read that mapped to only one spot. And we usually prefer to have 80% or more for the uniquely mapped read percentage. And for the average mapped length, sometimes it can be very different from the average input read length if the reads have a lot of bad quality reads or missing reads. However, since in this file we can see it's really similar to the average input read length, so we should not worry too much about the quality of the reads. And we also have the number of total slides, and for the number of slides annotated is 0 because I didn't supply annotation file when I run the star command. And however, I do have the number of slides that are non-annotated. And we also have mismatch rate per nucleotide and deletion rates and insertion rates. The other interesting section to look at is the multi-mapping reads. Number of read mapped to multiple loci is any read that is mapped to more than one spot, for example, poly A tail. And number of read mapped to too many loci is, by default, the value is 10. So if the reads map more than 10 spots, it will be categorized in too many loci. For the unmapped read is just generally the reads that either contains too many mismatch or reads that are too short. For example, the default is like if it's shorter than 2/3 of the read length is usually discarded as unmapped. So it's very important to look at the summary file and to see if you are able to trust the alignment output. If you feel comfortable with the alignment file, you can perhaps then use htseq to count the reads of each gene from the alignment files. Or you can also try Star Fusion, which is a package for detecting fusion transcript from star chimeric output. And there are pros and cons for using Star. First of all, Star is really fast. However, it requires high computational power. It probably would need 30 gigs of RAM in order to map for human or mouse genome. So you might need to take that into consideration. But overall, I would highly recommend people to use Star. And thank you for listening to my presentation today.